My name is Anthony Lozano, and this is my presentation on the Kalman Car Counter. It's an implementation of a computer vision traffic data collector. So what does that mean? That means I can process videos and find the cars in them and count them as they go by and produce traffic data. So why is this important? Well, traffic data is important to a lot of people. Civil engineers need it so that they can plan when to build new lanes on a roadway or change the timing on traffic lights. Policymakers need it to decide when to build, new bridges and when to add bus routes and mass transportation and new roads. Business owners might be interested in traffic data simply to find out if their business is going to have a lot of traffic near it so that they can get more money, more business. You can even use traffic data to do some environmental emissions estimation and other estimations. So what's the problem? Well, it's hard to collect good traffic data. The existing methods like these software tools, like the one I'm trying to design, are pretty expensive. Hardware tools like loop sensors in the ground or studs that can count cars that go on top of them, they require a road shutdown to install, they require hardware, and you have to damage the road to put them in, and there's some maintenance involved there. There's other kinds of sensors, pneumatic loop sensors you might have seen. They roll these pneumatic loops out across the road and it tracks the number of cars that go by. Those have some problems too. Foremost, you have to shut down the road. So shutting down the road in an urban area can cause a lot of disruption, especially at the time of day that you want to collect traffic data. Some other methods, you could have humans manually count the cars in the video or just stand at the corner, but a lot of humans don't want to do that. So can we track the cars in the video well enough to collect traffic data? Yes, we can. So the way we're going to try and do this is by building a computer vision analysis of the images in the video to track cars. We're going to take tracking of car data and try to feed it into a Kalman filter to predict where the cars should be going. If those predictions turn out to be accurate, we can say that we found the car, and we can count the car as it rolls off the screen. If we can make such a system like this, then it can save a lot of people a lot of money, and they don't have to buy an expensive system. And then anybody with a camera and a decent vantage point could collect and contribute to traffic data. So say a business owner doesn't have access to a county traffic database for traffic data. He could just go to the overpass and get the data himself. So how are we going to do this? There are a few steps we have to take. The first thing we have to do is remove the background from the video. What that means is we need to get only the things that are moving in the video, only the cars. It'll include things like birds, and the shaking of the camera will produce some other features. But background subtraction will help us find the features that we care about. So then we have to actually find the features that we want to track. And the way we're going to do that is with a Shi-Tomasi corner detector. Once we found those, we're going to feed them into an optical flow, which is a Lucas-Canard optical flow calculator. And then with those set of tracked features in hand, we're going to cluster the tracked features to produce a single data point. That single data point is going to be fed into the Kalman filters. We're going to assign a Kalman filter to each one of those clusters, and we're going to track those clusters as they move through different frames. And if we can track it when it runs off the screen, we call that vehicle tracked, and we can count it as leaving the scene in a particular direction. So the first thing we do is background subtraction. So background subtraction is a set of techniques for getting the foreground from a series of videos. The Kalman Car Counter uses the simplest approach, frame subtracting. So if I have a frame here and the hand moves, you're going to see white when the hand moves because this frame is different from this frame, but only right here. The rest of the frame is the same, so that gets subtracted away. Performing this operation will make it easier to find anything that's moving, particularly the vehicles. We'll see an example of how this works after the presentation. So once we have the background subtracted away, we're going to try and find some good features to track. The way we do this is with the Shi-Tomasi corner detection algorithm. How Shi-Tomasi works is it looks for corners, like this corner here on the poster would be a perfect feature to track. The way we define corners is when the sum of the differences, of square differences between the image patches, so this would be an image patch here, around that, is very high. This equation here shows the sum of square differences calculation, which could be estimated with a Taylor series that produces this matrix A here. That matrix, if it has large eigenvalue pairs, then we can say there's a corner there, and that's all we need. The Shi-Tomasi corner detector directly computes the small eigenvalues that it needs to find the corners. it skips the actual eigenvalue decomposition, which speeds up things because we're not really interested in edges, which is what would happen if you didn't have a pair of eigenvalues that were positive, but only one of them was and the other one wasn't. We're looking for two relatively large positive eigenvalues, and the Shitomase corner detector just skips straight to that. So the next thing we need to do is optical flow tracking. So once we have all those features, we want to track them as they move from frame to frame. So if we had features around this hand here and it moved here, we're going to try and calculate the velocity of all those pixels. And if we can come up with a reasonable velocity for all those pixels, then we can say there was a feature there and that it moved. So the way we do that is we should try and solve this system of equations. So the velocity of the pictures, or of the feature, is going to be v of x, v of y, and the pixels in the neighborhood of that feature are going to be q1, q2, q3, and so on. This system of equations is usually overdetermined. There's usually more pixels than you need to solve it. So it takes an estimation, and that estimation is good enough. It gets you there. And the particular implementation of this is a pyramidal Lucas-Canard tracker. The pyramidal one is going to allow us to only calculate this just on the new frame. We won't have to calculate all the frames before it. We can just keep a rolling frame continuing forward, and that speeds up things significantly, which is good. So after we have a bunch of track data points, we need to cluster them. We'll show an example of this also after this part of the PowerPoint here. We are going to cluster them using a hierarchical clustering algorithm. The hierarchical clustering algorithms automatically determine how many clusters are in the image and where they are. We're not too concerned about clusters merging or overlapping. The common filter should be able to handle a few missing measurements from a merged or an overlapped cluster that got moved a little bit, or maybe one cluster took some points away from another cluster. That will just show up as measurement noise to the common filter, and the common filter should be able to deal with that accordingly. So once we have these measurements, we need to assign them to common filters. Each measurement has to go to a different common filter. So how are we going to do that? We're going to take the distance between the cluster's mean, A, and the next prediction of the common filter, 1. So if we have a common filter 1 and we have a bunch of different points from the clusters, here's our prediction and points, we're going to go ahead and we're going to make a cost matrix. The distance between the point and the prediction is going to fill out all of these entries. We solve this, and then we're going to, with the Hungarian algorithm, then we're going to have assignments for each common filter. We'll still need to handle a few special cases. This matrix can actually be rectangular. There can be more entries in one or the other, more clusters or more common filters. If there's more common filters, some of the common filters will be lost. Also, any common filters with a cost too high to be considered a real tracked common filter, we're just going to throw those away. In my 1080p video, I'm saying a distance of about 50 pixels is too far away, and I'm throwing those away. If we have too many measurements, well, that's actually a very simple special case to handle. We just make a new common filter to track the new clusters that appear. And we want to track the new clusters as they appear so that we can track all the cars that come into the frame. Once we do this, we can actually start using the common filters. Yay. So we have a simple transition function, f. It's got x and y, and the change in x and change in y are velocity. Of course, x and y are dependent on the change in velocity, or the change in time with relation to velocity. We're saying change in time is dt. In this video, dt is going to be about 0.5 because it's 30 frames per second. So that means that dt is reasonable at 0.5 per frame. And I'm going to show you a few videos of the common filter in action. This first video is just a video of the overpass that I took. It's a hot sunny day in Phoenix, Arizona. You can see the cars going by. The camera shakes a little bit. This is because I'm just holding my cell phone camera. No special tripod or mounting or image stabilization is going on here. Just me at the overpass holding my camera as steady as I can. The overpass itself shakes, and these shakes might not seem important, but when it comes to background subtraction, we're actually going to see that they do have an impact on what we're doing. But it's not too bad. It's not something that we can't overcome. So let's take a look at what the background subtracted image looks like. So this is the background taken out of the image. And this is where we're actually going to be performing most of our corner finding and feature finding on. You can see that, yes, because the camera is moving, the noise from lanes and bushes and tree lights and barrels comes in. But the important thing here is that the cars show up really well and they have a lot of corners. That's what we're looking for, so that we can find the features that we want to track and we can feed those features into the Kalman filter. So now I'm going to show you what it looks like when we find the features and we cluster them. Here we have our clustering algorithm running. It's clustering these data points here, as you can see on the motorcycle. Those two clusters were the same, but then as the cars diverged, it was able to determine that there was two different clusters there. So those clusters would form a new Kalman filter, and that new Kalman filter would track the new car. This truck here is not exactly completely clustered, but we're going to ignore very small clusters. For this video, I ignore clusters that don't have a size of at least 2. So finally, I'm going to show you the Kalman filter in action. So these little blue circles are the Kalman filters tracking. You can see track that motorcycle and that car pretty well. Some of them spring into existence and quickly don't find where they're supposed to go, and then they fade out of existence. But mostly you can see that a lot of cars do get successfully tracked as they're going up and down the highway here. It has a little bit of trouble with the darker cars. That's probably the fault of the background subtraction algorithm that I've chosen. And sometimes it picks up a bird that flies by, as you can see there. Some really interesting things, though, is on the exits here, you can see it actually does pick up these cars, albeit temporarily. This one here it picks up briefly, but the truck goes by over here. This truck is actually tracked the whole time. It's just slightly tall enough than the trees, and that's enough for the Kalman filter with its noisy measurements to track the truck all the way up until perspective makes it too small to be worth tracking. So that's my presentation and my implementation of a Kalman Car Counter. If you have any questions, feel free to post them on the video comments or email me, and I'll try to answer them as best I can. Thanks for a great class, and I will see you guys next time.